Good morning, good evening, wherever you're from. My name is Pete Tatey. I'm the team leader for the Process Control Method Subject Matter Interest Group for the Aero Engine Supplier Quality Group. Um, and would love to welcome you all this morning to process capability for unilateral tolerances, including true position. Um, this is the third webinar that our subject matter interest group has offered, and we've got quite a few more coming up on the schedule, as we'll show you in later on in this particular webinar. If we could go to the next page, slide, please. So our lead speaker today, I'd like to introduce is Andrew Stout, who is a master black belt from Pratt & Whitney, Canada, Halifax Division. Andrew, along with being a master black belt, is the co-leader of our SMIG team and co-author of AS 13006 Process Control Methods, as well as the reference manual 13006 that provides the guidance around process control. Andrew also has been a member of AESQ in the standards developing since 2015. He's also a global trade manager and sustainability focal for Pratt & Whitney Canada. So next slide, please. So this webinar is being recorded. We will have Q&A. You can use the chat button, please, or the chat function. And but we will spend some good time at the end of this webinar to answer questions. So we'll try to do that without too much disruption to the speaker. But we'll see, depending on the type of questions. If they're quick answers, we'll look for a good break. If not, we'll save them for the end. Slide, please. So capability for unilateral tolerances. Why this particular webinar? We started off in December with an overview of what 13006 offers in terms of the reference manual. Now we're getting a bit into the technical detailed discussions, a bit into the weeds, if you will. This is one of those technical discussions that have been asked for. How do we deal with unilateral tolerances and process capability? Comes up all the time in our industry. So we're going to talk about what's written in RM 13006, how to analyze using statistical tools, such as Minitab and others, in conducting this type of capability analysis. At the same time, we want to promote always in these webinars the free documentation available to all AESQ suppliers available on the Aero Engine Supplier Quality website. Next slide. So in terms of the reference manual, RM 13006 provides guidance. There are no requirements in the document, but it provides requirements on it provides guidance on meeting the requirements of AS 13100, Section 9, which is involving process control. The reference manual spikes out 9 specific control methods that are most common, including the use of variable control charts where process capability analysis is quite prevalent. And today's discussion gets into the details on one piece of that, unilateral tolerances. 13006 supports AS 9145, which we're all required to meet, Advanced Product Quality Planning, and PPAP, the Part Production Approval Process. Next slide, please. What is the Process Control Method SMIG team? There are experts in the area of process control throughout the globe in the aero engine supplier quality community. We get together on a regular basis, and we're the curators of RM 13006, as well as manage the community of practice that's on the LinkedIn site and putting together these specific free training webinars that will be available to you constantly after today on the AESQ past event website. Again, you can see the link to the AESQ website. Make a shortcut of that because there's all kinds of great information for you available. You can see a little snippet there of our webinar schedule, what's been completed in green, what's going on right now, and what's coming up in the future. So we've got a very aggressive schedule for 2023. Next slide, please. This is the membership that makes up the SMIG team from the various AESQ member companies. And in fact, we just added Ricardo Banuelos from Rolls-Royce. So now we have 13 members of this team that's here to help the supply chain with the implementation of process control. The next slide. So where to get help. If you want any of the free reference manuals available, along with 13,006, there are many more, PFMEA, human factors, FAI, APQP and PPAP, and the list goes on. Go to the AESQ supplementary materials webpage. There is the link. If you want to, please, we ask you to join the community of practice on our LinkedIn site. You can see the link below. And in that particular community, you can also bring up questions anytime, and we'll try to get back to you in a timely way. So again, this is part of the community of practice, trying to help each other in this area of AS 13100 process control. Next slide. This is where I turn it over to Andrew, our lead speaker for today. So now let's walk through process capability for unilateral tolerances. Andrew?
Okay, thanks, Pete, very much. Welcome to the webinar. Here's a bit of the plan in terms of the reference manual itself. We'll be touching on sections 6 and 7, starting sort of an overview or perhaps a refresher of capability indices, without getting into too much detail, just some of the key points behind capability or before calculating capability. And then we'll dig a bit deeper, starting to get into some of the non-normal and then into true position. So we'll get deeper and deeper as we go. Hopefully we won't lose too many people along the way. And now it's also important, and we get into the true position, it's not really covered yet in the 13,006. It's a new material that we're looking at, we'll be discussing and potentially likely adding into a future update of the RM. So, bit of an overview first. Why does process capability matter? Well, in a lot of cases, your customer asks for it. He wants to know where your process is running, how it's running with some capability information. It gives you a chance to evaluate your process and also to determine the potential it has when you compare your PPK to CPK to CP, that type of thing. It gives you some ideas of where you have room to improve. And also, we know that we have limited resources these days, and we have to be careful how we spend those resources, where we allocate them, so it can help decide where to focus attention, perhaps on the lower capability ones. So, and bit of a refresher on the PPK values, or CPK would be similar, where a 1 is basically meeting the spec limits. 1.33 is a common measure where we'd like to be there, or maybe even better, 1.67, or 2 would be really good, right? And we're well within the spec limits, the lower and upper spec limits. So some other key principles of capability. First of all, we need to make sure we have good measurements, fundamental, right? That the value you get off your gauge is a combination of the actual value plus the measurement variation. And if we're not careful about that, we may end up rejecting parts that are actually good. So that's the story there. Process variation plus measuring variation equals your total observed variation. The next step is to visualize your data in a control chart or a run chart or similar is a good way to do that, where you may come across points that are far outside the normal values. And then you want to look at those and see if there's something going on there. Is it a typo? Did the gauge freeze up? What happened? So that's important to do that, of course, to understand the anomalies. And then, do you have enough data to capture the full process variation? Do you have some longer term variation going on that you need to capture to see the full story? And in a lot of cases in aerospace manufacturing, it's a challenge to get enough data. So there are some techniques that are covered in the RM on ways to get more data, especially if we're doing an MSA. Some techniques in there which I'm not covering here that can help you with that. Next step is to make sure that your data is in time order and to look at the plot, the time series plot. And there's certainly different ways to do that. Individual values, moving range, or X bar are a couple of good ways to do it. And here we're looking for trends. We're comparing against the actual control limits based on historic values, and looking for trends. Here's a trend going up, and we may want to understand that better. Okay, what's happening at the start of the process? So it's a great way to understand what's going on and to look for assignable causes. So here's another one that where we had something shift at this point. Okay, we need to understand that. It could be a good thing. Maybe we want the process to be running lower. So that's you know, looking visually at the data, very important in time order. Now, to be practical, we're trying to be practical as a writing team. We brought some of this into the RM to help. We know the real world is not so pretty, as it says here. So we are suggesting that in at least in some cases, it's acceptable to have up to 2 out of control points per 25. So if you have 25 points in a row and you have a couple that are just beyond the limit, I would typically say within 4 sigma. This is if the red is your 3 sigma line, you could have a couple points that are within the 4 sigma and still be considered adequate to get a pretty good estimate of your capability, like an early estimate especially. So there's some attempts to be more practical and realistic. So that's built into the reference manual. Now, basics of distributions. So very quickly, distributions vary in a number of ways. You know, the location, the how spread out it is, the shape. And we're going to be focusing quite a bit in this one on normal versus non-normal. So the red being normal, the blue being non-normal. Non-normal, the normal distribution, looked at in terms of a histogram, can provide information as well. That's quite valuable. And one tool to look at information is the run chart, control chart. But the histogram can also show when you have assignable causes acting, and we'll see some examples of that shortly. But it's very useful, and it's usually in my experience, I see around 60% of the characteristics that end up following this normal distribution. But that still leaves 40% that don't. So what about those 40%? Let's have a dig into that a little bit. Well, there's some bimodal ones. I've seen a case where we have a machine that had 2 fixtures. So one fixture is down here, one fixture is up there, and they're not. It's very hard to get them to make the parts the same. And you see on the normal probability plot that the dots don't line up with that center line. We'd like to have them hugging that center line to indicate we have a good fit for this distribution. In this case, it's the normal we're looking at, and it's not a good fit. The dots are way off that center line, where the outer red lines indicate the 95% confidence interval, roughly. So you can see visually very quickly, and this is an obvious one, usually it's not so obvious, that you have two distributions within the same chart. And you have to dig in. You don't want to try and analyze the capability of this. You got to, understand what's going on and separate out, find out what's going on before even thinking about doing capability. Skewed distributions, we'll be getting into this, or one-sided. So it's not symmetrical, not a normal distribution. You have a tail that goes off to in this case, it's going to the right, so it's right skewed. Could be due to the fact that this is a unilateral tolerance. It's flatness in this case, so flatness can't be less than 0. So we have a fair number of parts that are very close to 0, and a few that are further away, and then we end up with a distribution that's not normal. So if you look at it on the probability plot for normal, we got a poor fit. You can see it doesn't stay within those confidence lines, and it's nowhere near that red center line. So it's not so good. We'll see more about this in a minute. Truncated distributions, where it seems to be chopped off for some reason. There's a number of reasons how that can happen. Perhaps an operator is reworking parts to get them just within spec. Maybe this is your spec limit, and the parts are being reworked just to get them within. Once they're within, we're happy. We're not going to shoot for nominal because we might go too far the other way. So that's what you see sometimes for truncated. So distribution fit, very important before getting into capability, or as a key step towards getting to look at capability numbers. So again, if you have bimodal, the numbers here are kind of strange. CPK 1.4. That sounds pretty good, eh? 1.33 is kind of our target. 1.4, is that good? That's the black line there. But that black line doesn't really represent very well what's going on. And really the red line doesn't either. The red line is your PPK line, 0.53. That's pretty low. And so if we could just take one of these distributions, it would be considerably better than that. So need to look at the picture. The first step, does it fit well? Again, here we have the skewed distribution, and our CPK value at 0.9. Does that make sense? Well, we're trying to model a non-normal using a normal distribution, and that just doesn't work well. You can see that out here the distribution doesn't fit well, these outlying points. So that's not correct either. So a little more on assessing normality. Getting into that, there are some things to look at besides just the picture. I mean, the picture is kind of the first step, right? Does it look like it's normal? The next step would be to visually look at your probability plot. In this case, we're looking at the normal. And we see on this case, the points seem to follow pretty well within your confidence intervals. And we have some numbers up here. This is it happens to be the Minitab type output, but there's many different software tools available that can provide different statistics. A common one certainly would be the p-value. And for normal, we're looking at a p-value to be greater than 0.05. So here we're at 0.228. So that's bigger than 0.05. So it looks normal from the p-value point of view. What about the AD? AD is Anderson-Darling. AD, or sometimes it's called A double star or A squared. And we'd like to see that ideally less than 0.75. Here we have 0.481, which is less than 0.75. So again, we have that measure that says it looks normal. So a number of different ways, right? Visually first, and then the numbers. There are other statistics depending on what software you're using, or if you want to dig further, and there are some cases where resolution causes a problem with Anderson-Darling, and we can go to some of the other statistics like Ryan Joyner and what we call the Smirnov test, or some people call it the vodka test, the Kolmogorov-Shmirov, the KS. And also there's Shapiro-Wilk, and some software produces an AIC statistic as well. So there are other ways to assess. Okay, so the top chart, top data looks pretty normal. How about the bottom one? Again, its flatness doesn't look very normal and not a good fit. But what do our numbers look like? Well, we have a p-value less than 0.005, and p we want greater than 0.05 for normal, so it doesn't appear to be normal that way. We have an Anderson-Darling of 4, more than 4, we want less than 0.75. So again, the numbers say it's not normal. Okay, let's move on.
Andrew, got a
Yep.
good question. You showed on the prior slide, Anderson, Darling, Ryan Joyner. Do you ever see it where one says it is normal and one may say it isn't normal, where they disagree? That's a question from Lexia.
Occasionally, and I would look at it in the order that I discussed it. Really is visually first, and especially if you have the line, the capability line over it, it makes it easier to see it. In this case, we don't have the line; we just have the histogram bars. The first step there, and the second step being visually look at the normal probability plot. And does that visually make sense? Especially looking at the outer areas, which tend to be closer to your spec limits. Here we don't have a spec indicated, but typically we care more about the fit in the outer areas closer to the engineering spec limits or the process spec limits. So then I would then prioritize after that the p-value and then the others with less importance. Although Anderson-Darling I know can be off if resolution, if you see a stack of dots vertically on this chart, like a chunk here and a chunk there and a chunk here, that indicates a resolution issue, and Anderson-Darling will not be doesn't handle that well. And then I would go to the Ryan Joyner or the KS if necessary. But I like just quick and dirty, looking at the visually, and you tend to know by the type of feature what kind of distribution to expect. If it's a flatness, you're going to expect it to be non-normal. And you probably think that, well, in the past, the Weibull distribution has worked well for that, so I'll start with the Weibull.
All right, thank you very much.
Okay. So we're looking in section 7 of the reference manual, and just to talk a little bit about non-normal data. So the focus on skewed data due to a boundary condition is quite common. So our geometric tolerances, and we'll get into when we have more than one component, 2 or more components of variation, like the true position when you have an x and y coordinate. So we'll get into that. And there are many other causes of non-normality, some of which we've already touched on, but we won't go through that again. So we have what we believe is non-normal data. What do we do about it? Well, check your process. Make sure you understand that the data seems reasonable. You have enough data. You know, at least, well, at least 25. 30 is preferable or more, and to get a good analysis. Less than that, and then you may not be getting an accurate value out of the data. Next is to find a non-normal distribution that that provides a reasonable fit. And I find from my experience, I like the Weibull, but the Weibull doesn't handle zero values well, and this will throw people off all the time. They try and use Weibull, but it errors out because there's zeros, because zero is ideal, right? Zero flatness is perfect. And so occasionally you'll get zero values. But we have a technique, and it's documented in section 722, called the macadam shift. And it's covered up here, basically, where you shift the zero values by 20% of the smallest resolution value. So 20% of so it's a bit of a manual manipulation, but it can be done fairly quickly with Excel or Minitab or other tools where you take all the zeros and adjust them slightly. And it kind of makes sense if you look at in terms of the bottom here, in terms of the average of each range. So these, if you can see the little red ranges on here, the center of those ranges represent these values here. So that zero is not the center of this first range. This 20% value is actually the center of this first range. So it kind of makes sense. So it's not just fudge. It actually makes sense. So that's the shift, the zero shift, which allows you to use Weibull, and Weibull tends to provide a pretty good fit in most cases. Now, for doing capability with software tools, there are a few different methods. If you're using Minitab, it uses the Z-score method or the ISO method. The Z-score has to do with proportions, and the ISO method uses percentiles. So the ISO method, to give you an idea, if you're not familiar with it, in this case, we have a right skew distribution, like flatness, and we're going to look at the 99.865 percentile that we've determined previously from the probability chart. So it has this value up here, that's the 99.865, which we're going to call a distance B from the median value, the 50th percentile, your median value. So the distance from the median to the 99.865 is B. The distance from the median value to your upper spec limit, we're going to call A. The ratio of those two gives you a PPK value. So kind of different, right? That's essentially the ISO method. When you do it in your software, you can select which method you want to use. Now there are special cases which we'll get into shortly. Now, last resort is to transform the data, and I'm not going to talk more about this today, but it'll be covered in a future webinar, perhaps number 8, dealing with non-normal data, is to first try and transform with box-cox. What's a transform? If you're not familiar with it, you're trying to transform something that's non-normal into something that's normal. So when it's normal, then you can use your basic techniques that are done with the normal distribution. The only trouble with these transformations is that the data no longer reflects your normal measurement values, your inches scale or centimeters, millimeters, right? It's in something different, and it's a little bit hard to interpret. Can be confusing for people to look at it. So it's kind of what we identified as the last resort. Can be done, it has to be done with some care and an understanding of what you're doing. Okay, one other thing to mention here, when we're talking about standard deviation, it's not applicable if we're talking about non-normal distributions, okay? Because the sigma or SD applies to the normal distribution. So that's just something to keep in mind. Now, one-sided tolerances. Let's get a little bit more into that. A note you'll see in section 6 of the reference manual. So you won't get a CP or a PP when you have unilateral tolerances, because you don't have both specs, right? You may have an upper spec and not a lower spec, or you may have a lower spec and not an upper spec. That's the two cases we're looking at here. But you will get a CPK and a PPK based on either the CPL or PPL, the lower side, or the upper side, CPU or PPU, whichever you can calculate. Okay, so in this case, in case 1, the example could be shaft runout. So here, the shaft runout can't be less than 0. 0 would be perfect, so we have a physical limit. This is called the non-risk side. We're really more concerned with the risk side, or the upper spec limit, the maximum value, right? So that's our area of concern. Currently showing a normal distribution on here, but it could very well be non-normal, depending on how close it is to the physical limit. Case 2, where you have perhaps a min wall or some other measures like this, the risk side is now on the left near your spec. Okay, and we don't have any upper spec limit. So case 1, where you have the physical limit, we're not going to analyze it as a two-sided. We have to do something different. When calculating capability in your software, leave the lower spec limit blank, or if you can identify it as a boundary. Some software has a checkbox where you can indicate a boundary. So in this case, PPU, we're looking at the upper side is the risk side. What it tells us is the process likely to yield products with characteristics beyond the maximum allowable? And the formula, looking at the upper side, basically of the calculation, the upper spec limit minus the average, overall average, over the 3 sigma value. And so that's the PPK would be the PPU in that case. Now on the case 2, the lower, when you only have a lower spec, I mean, this could also be in things like mean time before failure or to failure or horsepower, where you want to achieve a minimum value and higher is better. So in this case, we're going to look at PPL, and it answers, is the process likely to yield products with characteristics below the minimum allowable? So we're looking at the average minus the lower spec limit over the 3 sigma value, and that forms our PPK value. All right, so those are the basic unilaterals. So before we get into true position, we're going to just do a quick review of maximum material condition, MMC, or it may be shown on the drawing as M in blue here, and this feature control symbol. Usually it's perhaps in a full circle on the drawing, but shown here with brackets to make it easier to record. So what is maximum material condition? It's a condition where the most material exists. The most material. Think about a hole. What's the most material? It's going to be the smallest hole. Or the greatest mass on the feature. More material, greatest mass. That's another way to think about it. So it's the minimum inside diameter or the maximum outside diameter. If you have M on the drawing, as the feature deviates from its maximum material condition, that amount may be added to the positional tolerance. So in this case, Up here, we have a M which allows us to modify that 60 thousandths. If this is inches, 60 thousandths. I can gain some tolerance from the feature size as it moves away from its, in this case, it's an inside. So as it deviates from its smallest diameter, then I can add that difference on to the positional tolerance. So, and this may seem basic at this point, but it's important to understand it when we get into the more complicated values in a minute here. So the min ID, calculate that. So it's a 2-inch plus or minus 40. So for the min size, take off 40, 1.06. If the actual is a little bigger than nominal at 2.01, the MMC bonus, subtract the 2.01 from the minimum, or subtract 1.06 from the actual, gives 50 thousandths of MMC bonus. So that's what we're calling MMC bonus. How far are we off of the MMC condition? Now, be very careful with the units here. Here, we're talking about diameter. We're working with diameters here, right? This is a diameter. This is a diametral true position. So often, though, we want to take it into our radial mode, so we divide it by 2. So in this case, we'd have 25 thousandths of radial MMC bonus. So now, with that, I can find my true position with bonus is the basic 60 thou plus my 50 thou diametral for 110 diameter, or again, converting that to radial, 55 thou total tolerance in a radial mode. Hope that makes sense. Moving on, we'll use that in a minute. So true position is kind of a special case, and that's why we've had many questions asked, and there are many different methods out there to analyze capability for true position. So from a very common one is the true position radius, just working with the radius alone. So if we say our distribution is like this, and this is many points, we don't have quite that many probably. This is like 10,000, the little red dots. We'll say we're looking at the X and Y axis for this position, but it could be any combination of axes directions. But for this presentation, we'll just talk about X and Y as our axes. So taking the true position radius of all these points, X and Y coordinates, square each one, take the square root of the sum, gives us a true position radius. And then we could plot that on a chart similar to the one here. And it shows that if you look at it visually, doesn't look quite normal. We got a little tail on the right-hand side here. And so that is quite typically non-normal. Okay, but other methods that can be used is an adjusted true position, a residual tolerance, a percent of tolerance, effective size to virtual, and the area method. The area method will be my focus coming up right after this. So the true position radius value, first of all, is quite commonly done and fairly straightforward. But something to keep in mind that the Weibull distribution, which is shown here with the dashed line fitted to it, looks pretty good, eh? Pretty good fit. But that only really happens, you only get a really good fit when the X and Y are on target. So your process is centered on your true position target. Once you leave that, once the process shifts a bit off of the 0, 0, then it's a little bit more tricky and the measure is not quite so good. Your fit is not so good and can be a problem. So individually though, the X and Y axes, if you look at the values for variation on your X and Y, they will usually form a normal distribution. So we can use the normal rules that that we talk about, including sigma, for individual axes. So that's where we're going to see how that works in a second. Whereas the true position radius is almost always non-normal and requires a little bit more care and attention. So true position radius, there's the formula. True position diameter is simply twice the radius, of course. So let's what's the downside of some of these methods? Most of the methods, if we have two cases, in this case we have the tolerance area indicated with green, and X and Y axis is shown, and I have a number of measurements. It could be different parts produced, and they're all in the same quadrant in this area here. So we'd have, you can imagine a capability, X and Y capability. Now it'd be a certain value, right? What's the radius? The radius would be average of, you know, whatever this is around here. Now, how would that differ over here? Well, I've got a group here, and then something changed. I got another group here, something else changed. I got another group down here, and another group over here. So I got some variability going on. Does that change the radius value? No, right? They're all the same radius. So in this case, and this is a, you know, you probably wouldn't see too many like this, but just to illustrate the point, the capabilities would be the same using the TP-RAD method and many other methods that are indicated back here. Don't consider the angular position of these points. So it's a bit of a drawback. Doesn't capture the full variability in most of those methods. So that's why we're going to look at the area method. So it's not the only way to do it, but it's perhaps a newer way to look at it, and something that we're going to be discussing as part of the ongoing evolution of the reference manual 13006. So the advantages of the area method, it's kind of a good way to visualize and to actually represent the true situation when you have a true position value. And there's some comments from different posts that I won't get into too much, but it kind of supports the methodology. And this is based on fairly well-known authors that are commenting about it. So let's start with the basic look. So green is, again, the tolerance value, and we're going to look at it in terms of a radius. So the radial tolerance, we're going to give a capital R. So capital R, the tolerance radius. Now the red circle represents the 6 sigma variation of the actual values. So the points there, the 6 sigma of those is this spread. Now half of that, 3 sigma, or in this case 3s, because we're talking about the longer term variation. If we want to look at process performance, or PP, we're going to look at S, and S, as a reminder, is you know, this little more elaborate formula, taking the difference between each value and its average, the average value, squaring it, sum them all up over n-1, take the square root. That's S. So we're going to talk about these values a lot. The R is the tolerance radius. The little r is the process radius, which can also be thought of, or in perhaps more detail, as the 3s max x and y. So what's max x and y? So if you think about your different axis direction, if you just look at the values, the difference on the x-axis, you can imagine a certain distribution, a certain variability. The variability on the y-axis may be a bit different depending on the machine, right, and how the machine's working. You may see different different variabilities. So we're going to look at both of those variabilities, and we're going to take the worst one. Whichever one is higher, we're going to use that to be more conservative. So that's the max of x and y values. That's why, and that's how we create this 6 sigma diameter, or 3 sigma radius, or 3s to be more exact. So that's the 3s max xy. So we're being conservative. Now, in reality, yeah, we really probably should have an ellipse on here because the variability is different, but that would involve even more complicated mathematics and maybe something that could be looked at for the future. But we'll start with a slightly conservative approach and use the bigger variability, whether it's x or y. So over here now, so PP is the tolerance over the process spread. In this case, the green circle is the tolerance region, the red circle is the process spread, and we're looking at area. Area is pi r squared, the radius of the circle. So PP, area PP then is pi big R squared over pi little r squared. Right? The pi's cancel. And we can also show that as big pi, big R squared, the tolerance radius, over this value that we called 3s max xy squared. Right? That's the squared. So big R squared over little r squared is the area PP, ratio of the areas, right? Straightforward, hopefully. Moving along. Oh, you can also sort of visualize this up here in a kind of a 3-dimensional manner, right? So representing the points, more of them are in the middle region, fewer and fewer as you go out. So that's just to give you an idea in terms of a 3-dimensional view. Now, taking the same idea, we're going to go a little further. So the green, again, is the tolerance radius, the big R, the red circle being the 6 sigma diameter, or 3s radial zone, little r, is that radius there. So now our process is no longer centered. Back here, we were on center. Wrong way. Now our process is off center. No longer on the 0, 0. So it doesn't change the PP value though, right? It's still the ratio of the areas and the same formula. So that's just showing this revised model now. And we're going to build on this to understand. So next thing we need is the distance from this actual center of the average of all these values to the 0, 0, the target or nominal center line. So we're going to call that K. So K is the square root, sum of the squares of the averages of the x and y values. So that's the distance from the 0 to the center of our actual circle. Right. Now we'll build on that. The next circle out, this sort of yellowish one, is what we call the consumed process variation diameter zone. The consumed. So you see that it touches the outer edge of this the process variation circle. Okay, so this is what we're calling the consumed process variation. And what's the radius of that? It would be the K value plus the little r, K plus little r. And then for the area PPK, we're going to be looking at the r squared, which is your tolerance radius, this one here, over that K plus R radius value squared. or we can show it in showing what the K is actually this, and the R, little r, is actually that. Same thing, a little more complicated looking for area PPK. And just remember that in this case, we're only looking at the upper. There's no lower side. So in terms of PPK, we're looking at PPU, which we'd normally consider in the basic formula, upper spec limit minus the X bar over 3S. So we're trying to do the same thing here, only working with areas. Moving on, the next step is, okay, we're adding the actual true position variability plus feature MMC bonus variability. So now we're getting into bonus tolerance. Remember our discussion on bonus? We can, depending on the actual size of the hole, if it's an ID or an OD, we can gain bonus MMC. And so we can apply that now to create and actually use a pooled method to create this 6S diameter zone, which combines the true position variability and the MMC bonus. Okay, so that's this new circle. And we also need to create a true position feature MMC bonus diameter zone. So that's this outer purple zone that we compare against. So now we're comparing the orange circle here against the purple circle here for that area. So area PP with bonus. One thing to keep in mind is that typically the bonus value is dimetral. So then we need to take half it because we're working with radius values here, right? We're working with the radius values. So we got to keep that straight by taking half of that bonus value. So there's the same R we had before, the tolerance. Put those two together and square it is the top. So that's representing this this orange circle divided by 3 times the S max XY plus the bonus associated bonus value squared, and we add them together. We can add them as the square of S value is like a variance. So this is the adding variances, taking the square root of that, brings it back into the same kind of units. So we can show it in different ways, same sort of thing, depending on how we express it. But basically, that's the formula. We're comparing those areas, the orange area that includes the bonus with an area that's related to the tolerance that includes bonus. And we end up with this kind of nasty looking formula, but it's basically something relatively simple, but adding the bonus values in. And so here's a summary of those formulas, the four formulas that we've just talked about, either with or without bonus. Now, what do you do with that? How can you work with that? Well, there are some techniques that are available, some tools that are available. In this case, it's using what some people call a pro steer chart or a thumbnail chart to be able to plot the values. So in this case, we're interested in looking at the diameter, the x-axis, the y-axis, the true position diameter, and also the combination of those. So we have a chart that'll show us each of those values, each of those axis values, the combined value, and down here the actual plot in an XY frame or whichever axis you want. So you can monitor your process quite nicely, and the person running the process can see, oh, it's my x-axis that's the problem, or it's my y-axis that's the problem, and you can see, okay, it's shifted in the upper right quadrant. I need to make a shift back down somehow. I need to look at that. Something's changing, and you can see the direction. Pretty cool, huh? Okay. Now to calculate the capability, you take those formulas, put them into an Excel spreadsheet with a little bit of graphics built in to be able to simulate kind of what I just showed you with the different circles. The green being the tolerance, the red being the process, purple being consumed. So in this case, there's no bonus tolerance, and it comes up with an area PP, an area PPK, after just entering the values for the diameter, the X and Y values, putting those all in here, and it comes up with the calculations automatically. Similarly, if there is a bonus value, if you're looking at, or if bonus is allowed, you want to take advantage of it because it gives you more tolerance. And so this spreadsheet handles that. It takes into account the actual diameter and applies it to the area, and comes up with an area PP with bonus and an area PPK with bonus, and adds another line onto the chart. It still shows the actual values, so you can see how they're distributed. So I'd like to recognize the developer of this method, being Paul McAdam, who's now retired, but he was a Pratt & Whitney Canada Quality Fellow. We did almost all of the development on this method. It was based on some existing discussions and points that were out there, but he put it together into this format essentially and developed it a lot further. So to sum it all up, looking over the overview of what we covered today, make sure you have data that you can trust. You have a good MSA, measurement systems analysis, and that's not easy. That can be quite involved, but it's essential. Have enough data to capture the full process variability. Make sure your process is stable. So we have different ways to do that. At least run charts, but control charts are preferable. Choose the correct distribution. Not always easy, but make sure the distribution is reasonable. Don't just, you can run, if you're running Minitab, you can have it pick all distributions, and it can come up with some weird distribution that really is out there and may not make sense for a manufacturing type process. So pick the correct distribution. Choose the appropriate capability indices to evaluate your process. PPK is preferred over CPK, but it's good to compare the different indices and see where the opportunities are for improvement. And if it's true position, maybe consider investigating the area method. Track and improve, and go and do it again. All right. Back to you, Pete.
Fantastic, Andrew. And we'll take some questions in a moment. And so just to put a lid on this particular webinar, prior to the Q&A, we have some more coming up. And so coming up next will be on March 8th, led by Paul Gorg, PCC. Quite opposite. This was a very highly technical, analytical uh, uh, um, uh, discussion. On March 8th, it'll be more on the use of non-statistical process control methods, error proofing, methods that do not require the use of statistics. That's one thing in the reference manual. It talks about different types of process controls, not just those that are statistically based, but those that are non-statistically based. Then we'll talk about another non-statistically based technique after that called pre-control, the power of pre-control. That'll be coming up in April. And then a 1 hour process control assessment. That'll be in May. I'll be leading that one. And that's basically, it does not take a real lot of time nor hours or questions to understand whether someone has a process control system in place that'll meet AS 13100. So we'll walk you through the 10 key questions for that. And so that's coming up. Next slide, please. And again, all of these are, you can see and register if you go to the AESQ website, upcoming events. And that's what you would click on to get to these future webinars that you can register to. So now in terms of Q&A, Andrew, we had a couple of questions relative to the spreadsheet. You probably could have predicted that. Are these spreadsheets available? Can we make them available? I did respond saying this is something we can discuss at our SMIG team meeting this Friday and talk about, what would it take to make that available.
Yes.
I don't know if you have any comment on that.
Well, I think we can make it available, but I think we need to review it first, make sure it's
Yeah.
100%, that our SMIG team is all good with it, and then incorporate it into the RM and have the
Okay.
have these spreadsheets or the spreadsheet available to go with it.
Yeah, and under supplemental material, we constantly will add new tools to that. So to the right of the link where you would click on RM 13006, you'll see some templates. We just added one on a guide sheet that our team member Shalish Shinde from Rolls-Royce prepared. And the team reviewed it, tweaked it a little bit, and now we posted it on that particular supplementary material website. So yeah, we'll take this up Friday, Mark. Thank you for that question. You also asked, is there any way to do this in Minitab? It's a good question.
Not the area method, not yet.
I
Although I
hope
think
someone
I'll
from
talk to my
Minitab was
Minitab.
on.
I'll talk to my Minitab friends about adding it. I've got some
Yeah,
contacts there, and
and that's
I think
something
they
maybe.
should be looking at it.
Yeah,
It's a good
yeah,
question.
very good question, and that might be a worthy meeting for our SMIG team to have with Minitab. So we'll take that down as an action. Will you be sending us these 40 slides or a link to them? Howard, great question. No, there's no need for us to send you the slides. You'll access them in a week. They will be on when we go to the AESQ website and you click on past events, you'll see all the webinars. It will not only be the slides, but you can click on the video. So that way, if you ever want to review this video, go through the material again, share it with people in your plant, you have that ability to do it. So good thing is we don't have to be sending out big emails with all these slides. They are available on the AESQ website and they are free. Let's see. Yeah, would you recommend any webinar for MSA studies? At the moment, I don't know if there's anything posted. Quite honestly, we'd have to go look on the upcoming events and on the AESQ website to see if the SMIG team for MSA has anything coming up. They may have some past webinars that they did. So I would invite you to go to the AESQ events tab, click on the past to see if the MSA team has anything there, or if they have anything coming up, click on the upcoming events.
I think the MSA team is a little behind the process control team in terms of getting webinars going. So I don't think it's there yet, but we will be.
Yeah, and we've been we were kind of in the planning mode last year. So our team did not get out there with webinars until this past December, but now this is our third. And as I mentioned, we've got a number of them coming up. So the machine is rolling now. But we'll check into that. Okay, so Mark from Crane Aerospace has a really nice comment here and question. We do the evaluations, but end up having to do X and Y separate capability assessments, but cannot implement the bonus tolerances allowances. And so no question there, Andrew, just a comment I thought was interesting.
Yeah,
They're looking at just strictly the different components, which, as mentioned, are expected to be normally distributed, not the composite true position. I was wondering that myself as I was watching your presentation. Would it be of any value to look at, the PPKs of each component? And if those PPKs were 133 or more, would it be assumed the true position would be where we want it to be?
it's a little tricky because it's a combination of X and Y to determine the position of a value. If you look at only the X's and only the Y's, I don't think it gives you the full picture. I'm not sure that would add any value really.
Yeah.
It makes sense to track the X and Y positions, like to have a control chart on them or a run chart at least, as far as understanding what's going on. But as far as the capability, I don't know if it adds any value.
Well, your control chart, where you had it broken up into X and Y and the true position, really is an excellent visual, especially for a manufacturing engineer. That might tell them exactly what adjustments to make in a program that might have been off. But it's a lot of power in the visual on this particular pro steer chart.
Yeah.
Let's see. That's all the questions we have up to this point. Are there any more? If not, we'd like to thank all of you for your attendance and look forward to seeing you again at next month's Process Control Methods webinar. And again, thank you for your questions. And thank you, Andrew, for leading us today through this technical discussion. May all of you have a great rest of the day. Take care, everyone. Bye now.